Okay, I just press the recording button and then I will put it as full screen mode. I hope everyone can see this, right? Okay, so let me just double check whether this recording is going on. Yeah, it's going on now. And then if you have any questions regarding the material or anything related to this topic, feel free to interrupt me. So welcome to the introductory section of Diophantine M tuples and elliptic curves. Hi, I'm Seoyoung Kim. I'm at Queen's University in Ontario, Canada. And if you have any questions or comments, please send anything to this email address. So let me start by defining what Diophantine M tuples are. But beforehand, I will try to introduce some details about this class. Namely, this project is jointly with Tryon Hammond. He's a graduate mentor, and then Steve J. Miller, who is also another mentor of Polymath Jr. But because what he did before with his students are related to this project, so he will sometimes drop by to our meetings too. So yeah, so that's a short introduction to this, how this is going to be managed. So yeah, what are Diophantine M tuple? So a Diophantine M tuple, which was first studied by Diophantus of Alexandria, is a set of M integers with a property such that any product of any two distinct elements in a set is one less than a square. And then one of the example of that is this set 1, 3, 8, and 120. So why is that Diophantine, in this case, 4 tuple set, right? Because it's a set of 4 integers, right? Well, we can calculate some products of distinct numbers, right? Then you can see 1 times 3, which is the first distinct number, right, is 3. And then, and then we know that is equal to 4 negative 1, right? And then that is equal to 2 squared negative 1. And then here in the first example, we know that the product of the first 2 distinct elements is 1 less than a square, namely it's 4 minus 1, right? And also similarly, if you multiply the second and third element in that set, what we get is 3 times 8, right? So 24. And then you can see that is equal to 5 squared negative 1, right? And also similarly, if you multiply 120 by 8, then what you're going to get is 960, right? Which is 961 negative 1. And therefore, I will let you calculate what 961 is the square of. And then, I forgot to mention about 1 times 120, right? And of course, that is equal to 11 squared negative 1. And then therefore, this set 1, 3, 8, 120 defines an example of 4 Diophantine tuple, right? Is this definition of Diophantine M tuple clear enough? Okay, if I don't hear anything, I think someone wanted to say something. Okay, some background noise. I can see.
Could we multiply? Oh, sorry. I wanted to ask whether we could multiply 2 numbers, the same number by itself, but I just read that it's 2 distinct. I'm sorry.
Right, exactly. So if you multiply the same number, then say you're going to get 3 multiplied by 3, right? And that is 3 squared, and then it is not 1 less than a square, right? Because 9 itself is a square, and therefore it doesn't satisfy our property, right? And that's why in the definition, this 2 distinct condition is important. Okay, so Diophantine M tuples is as such. And then we can kind of generalize this one part here in the following way. And then we call this definition to be Diophantine M tuple with property Dn. So the way we define this is by, if you have a positive integer n, we say a set of natural numbers S, which is A1, A2, up to AM is a Diophantine M tuple. So here the M is the size of the set S. With property Dn, if two distinct number AI and AJ in the set S is a perfect square modulo n, right? It's less than n of some square, right? For any distinct I and j. So that is the definition of Diophantine M tuple with property Dn. And then like the set which we saw in the previous slide, namely 1, 3, 8, and 120, is a Diophantine 4 tuple with property D1, right? Because the difference between the product of two distinct numbers is 1 in that case. So in that case, our n is 1. So that's what I wrote here. So the previous quadruple 1, 3, 8, 120, which was, by the way, discovered by Fermat, as property D1. Okay, so that was the very basic example, which we can easily compute. But how about whether there are any cases of n different from 1? Another very famous example is by Diophantus. And then he first studied the set of numbers and then found the quadruple 133, 68, 105 with the property D256. So in that case, by definition, what we should be able to see is that if you multiply, say, 33 and 68, which are distinct numbers in that set, right, in the quadruple, then if you add 256, then you should be able to get a perfect square, right? Because that's the definition of a set of m numbers with property D256, right? So that's the example discovered by Diophantus. I'm not going to compute like 68 times 105 plus 256 is square. I think I will leave that as an exercise to you after this talk. But believe me, yeah, that's just how what Diophantus found. And as you can tell, that probably this question can really date back to quite early. Okay, cool. Someone already computed that 68 times 105 plus 256 is 86 times 86. Thank you, Todd. So yeah, that's the example by Diophantus. And then from this all this definition, what we can ask, well, I mean, there can be quite a lot of questions, right? But one question can be, can we find infinitely many Diophantine M tuples of any size, right? Or even getting some sort of examples would be very interesting. And that kind of also tells that maybe it should be kind of tricky to find examples. Well, actually, it turns out to be true. And then that is somehow related to the geometry. But, and then the geometry is as follows. I don't know whether that many people in this introductory talk have learned anything about elliptic curves or even have heard about. So elliptic curves are a geometric object, which is of the form y squared equal to x cubed plus ax plus v. Or more clearly, maybe the way to put it is elliptic curves are normally, we say, curves y squared equals to fx, where fx is a degree 3 polynomial. So degree of f is 3. So this is what we usually call as elliptic curves. So so the thing is, if you see a Diophantine M tuple, so namely if your set A1, A2 up to AN satisfies the property Dn, then for AI, which is greater than when your I is bigger than 3, then it yields an integer solution to the Diophantine equation, y squared equal to a1x plus n, a2x plus n, and a3x plus n. Why? Well, say if you have A4. So if you have A4, then what you are going to get is, by definition, A1 times A4 plus, because you have Dn property, that should be a square, right? That should be a square S squared. And then your A1 or A2 times A4 should give you another perfect number, right? So let's say T squared, and then A3 times A4 should give you some number R squared minus N, right? And then because of that, if you multiply all those things, then what you're going to get is STR squared on the left-hand side. And then that's how your X, when it's equal to A4, will give you an integer solution of this elliptic curve. Namely, the integer solution should be A4 times STR. So that would be an integer solution of this elliptic curve. And therefore, what we know is that the Diophantine M tuples, finding Diophantine M tuples, is actually equivalent in its complexity. So I'm here kind of alluding some important aspect, but I'm not going to kind of talk about in detail about it. But what we know is that in its complexity, it's equivalent to finding an elliptic curves with integral points. So if you know Siegel's theorem, what's known is that integer points of elliptic curves is finite, and therefore, because you have this finiteness in its complexity, if you have Diophantine M tuples, then you can get integral points on the elliptic curve. And then also, if you find all integral points on the elliptic curve, then there are, because there are so finitely many of them, you can kind of filter out Diophantine M tuples. Yes, Watts?
I was just wondering, here the correspondence between the integer solutions and the tuples is not one-to-one, right? Because
it's not
maybe we have
one-to-one. It's not one-to-one, because especially because we are assuming our Diophantine M tuple to be positive numbers, right? And then your integer solution can be also negative. So definitely we are not one-to-one. Any other questions?
Yeah, I'm just wondering, why are we considering the equation of degree 3 instead of, for example, 4 or 5? Because it seems to me, whether you change the degree, for example, if you change it to y squared equal to, I don't know, like a1 plus a1x plus n to a say akx plus n, that still works, right? Like it's still a
Right.
necessary.
So yeah. Thank you for asking. So you're asking why the degree of this part should be 3, right?
Yes.
Yeah. Well, it's because that's elliptic curve case, and then the only reason why we are taking care of this is because there are so many things known for elliptic curves, and that's the only reason, because we want to use the theory of elliptic curves. We are using, we are just considering the 3 parts or 3 factors of but integer solution. But you're absolutely right. You can also consider a polynomial of higher degree. Then what you're going to get is, instead of an elliptic curve, you're going to get a hyperelliptic curve. And for that, you need much more background. But it really depends on your background. If you're used to hyperelliptic curves, I would love to work on hyperelliptic curves at the same time. But for now, I think we are going to be happy about elliptic curve in this slide. But actually, in a couple of slides after, I'm going to mention about hyperelliptic curves, case 2. So I hope this answers your question.
Okay, thank you.
Yeah. So in fact, if your set is larger than 4, elements, then you can also add like a4x plus n and a5x plus n and so on. Then you are going to get a curve which looks a little more complicated than this one. I believe there are also other questions too.
Yeah, I was wondering, so you're saying the complexity is equivalent, but what exactly is the complexity?
So here, the complexity is equivalent in the sense that the integral points on elliptic curve is finite.
No, sorry, I more mean to which complexity class it belongs to.
Oh, well, the complexity of finding Diophantine M tuples, if that makes sense. Like also in terms of computation, the complexity should be the same because it's exactly the same problem.
Okay, yeah, I understand it's the same, but can you say something about the complexity class it belongs to?
Yeah, you can also understand it that way, or you can also understand that in the sense that it's an equivalent question to ask, which can answer one to the other.
Okay, thank you.
Yeah. I know there are two more participants. Yes.
I was just wondering, like, if having coefficients, if we expand this elliptic curve, like the coefficient of x cubed isn't actually going to be 1, will that cause any trouble? And I was also wondering, like, you said it's equivalent. I can see one direction that, having a Diophantine equation gives rise to an elliptic curve. Is the other direction also equivalent?
So it's equivalent in the sense that integral points on elliptic curve is finite, right? There are finitely many of them by Siegel's theorem. And then if you find all the points, then you can, because there are finitely many of them, you can kind of filter out what are the Diophantine M tuples pretty easily in that finite set, if that makes sense for you.
It does.
Yeah, good.
I have a quick question.
Sure.
So is there a specific reason why you use the first 3 elements as like A1, A2, A3 like times X, or can you use any of the elements?
You can use any of the elements.
Thank you.
Yeah, sure. More questions?
Yes, please. You said no, it's equivalent in complexity. And you said that you mean by that integral points to which the curve is finite, right?
Sorry?
Okay, so when we were talking about the complexity, and we said equivalent in complexity, we said that these are the integral points to which the curve is finite, right?
It's more like the integral points of the curves is, there are finitely many integral points on the curve. But because of that, what we can say is the complexity of the question is the same. I hope this answers your question.
All right, thanks.
Sure. Are there?
Yeah, I have a quick question.
Sure.
I think you expressed that you could, that you could write the tuple as a concurrence. So I guess for the one that we had an example 138, 120, you could do x squared is congruent to 1 mod 1. Is that the way I'm understanding this?
Mod 1 is kind of weird, right?
Right.
Yeah,
So what I'm trying to say is there a way, or do we express the equation on the screen through modular arithmetic as well, or is that where we change?
Right. So if you have if you kind of if you consider like modulo n of this curve, then that curve will be just y squared equal to a1, a2, a3x cubed, right? Which is a degenerate curve.
Okay.
So in that case, I guess you can't really make use of the theory of elliptic curves. So I'm not sure how interesting that case can be, but I don't know. Maybe there's something interesting to say about that. But for different modulo prime p, then that would be interesting to study. And indeed, for studying an elliptic curve, you tend to study modulo P, right? So
Okay.
yes, we are going to think about that too.
Okay, thank you.
Yeah, sure. 2 more questions. That's good that there are a lot of questions.
So I'm thinking about this. I'm looking at this, and it seems like, just so I can understand the framework, are we thinking about this in terms of if we have a Diophantine 3-tuple with property d of n, and we encode it as this elliptic curve, we can then find additional integral points on the elliptic curve in order to extend the 3-tuple, or are you thinking about finding elliptic curves with integral points and then basically kind of factoring the f of x?
So yeah, it
get something
goes
of
on
this
both
form?
ways, right? Because if you have 1, 2, 3, like A1, A2, A3, then you can kind of extend that triple to a larger triple if you find more integral points, which means that finding a Diophantine M tuples with size M, where the size is big enough, can be a very tricky computational problem, right? But also, if you find any examples of an elliptic curve defined over integer ring, and then at the same time, if you find an integral points, then that will serve you also as an instance of Diophantine 3 tuples, right?
And just to
Or
make sure I
even 4
understand,
tuples.
just to make sure I understand, it seems like if you have an elliptic curve with integral points, you get like A1, A2, A3.
Right.
You're going
After
to need
factorization.
after factorization. Do you still need to check that A1, A2, and A3 satisfy the property with respect to each other?
Right. Yeah, you still need that, right? Because your A1,
Okay.
A2, A3 should be distinct.
Should be distinct, yeah.
Yeah.
But if you have them distinct, is it automatically the case that A1 times A2 is n less than a prime, or
not necessarily, right?
Okay.
Yeah.
Okay.
Yeah. Because say, having a square here doesn't necessarily guarantee that all factors should be square, right?
So I guess thinking about it, it sounds almost like the approach we're taking, or the algorithm we're applying, is find an elliptic curve with some number of integral points, and then basically we have finitely many integral points,
and because of that,
we still have to check each one, but
exactly,
it cuts
but
down
because
from having to
there
check.
are finitely many of them in its complexity, it shouldn't be too difficult, right?
Instead of having to deal with infinitely many points, we have
it
narrows it down.
Exactly, yeah.
Thank you. Thank you so much.
Sure. Any more questions?
Yeah, I have a question.
Sure.
So from my understanding of elliptic curves, it's not necessarily always going to be the case that they will factorize into sort of 3 factors like this. Am I wrong about that? Or?
After a field extension, you can factor like that.
Okay.
Yeah, but not over integers necessarily.
What was it you just said? Sorry. After what extension?
Field extension. So if you consider
right.
complex number field, right? Then of course that's algebraically closed fields, so you can always factor in linear terms, right?
Yeah. Okay. Yeah, I was just wondering if, because it felt to me like you wouldn't be able to apply this to an arbitrary elliptic curve.
Right. Yeah.
But no, I see what you mean.
Yeah.
Thank you.
Yeah, there are so many questions. Sure, please go ahead.
I had a quick one.
Sure.
So when you say like equivalent in its complexity, are you kind of talking like roughly in terms of like kind of like algorithms and almost like just the time? Okay, so then I was just trying to understand what roughly the two kind of computational problems are. If I'm getting this correctly, it seems like the first computational problem is determine if a given M tuple has some Diophantine property. And then the second problem would be from the set of all from the set of determine if a given elliptic curve exists in the set of elliptic curves that have integral points.
Right, yeah, something like that.
Okay, and essentially what we're saying is these two sets are equivalent in computational complexity.
Yeah, well, actually, you know, I have to kind of modify that a little bit because I'm starting here after having like Diophantine triples, right? And then starting from there, kind of asking whether one can extend the set. And for extending the set, one needs to kind of compute the integral points, right?
What do you mean by extending the set?
So it's if you
throw any
have
more
like
things in it?
A1, A2, and A3. So if you consider like the first example, 1, 3, 8, and 120,
Okay.
then already the smaller set, 1, 3, 8, which is a triple, already determines the Diophantine triple, right?
Okay.
And then with the triple, you can determine the elliptic curve y squared equal to x plus n, or x plus 1, 3x plus 1, and 8x plus 1, right? And then in order to find or extend the set, namely by adding the element, in order to find such thing, one alternative way to attack the problem is to find the elliptic curves with integral points, right? Which is 120, comma, the right kind of square number, right, for your y value. So the computational problem should be stated a little differently in order to really kind of claim about the equivalence.
Okay.
Yeah, but in this case, equivalent here is a very rough sense. I didn't really intend to be anything so rigorous about this talk, but yeah. So yeah, and then, you know, and then therefore you can kind of imagine that finding bigger Diophantine M tuples is equivalent to finding an elliptic curve with many integral points, right? I hope this is clear statement for people. And then what one can also expect from this equivalence is that because finding an elliptic curve with many integral points is quite hard, and then therefore you should also be able to kind of think that finding bigger Diophantine M tuples is pretty hard computation too. And indeed, one question can be, is it also possible to have a Diophantine infinite tuple for given any n? So that can be an interesting question to ask, right? Do anyone have an answer to this question?
I don't think you can.
Why not?
Could violate the theorem which you said, right?
Yeah.
Which
Finitely
theorem?
many integral.
You can only have finitely many
integral
integer points.
Right, Siegel's theorem, right? Yeah, so yeah, actually it is not possible to have such Diophantine infinite tuple. So thank you. So yeah, I can tell that some people are maybe already used to elliptic curves. That's a good sign.
Sorry, can you repeat why is it not possible?
Oh, it's because for given A1 and A2 and A3, there's a theorem that there are only finitely many integral points on an elliptic curve. And then therefore, you can only have, finitely many integral points, and then therefore you cannot extend the set very much. Okay, so that's its connection to elliptic curves. And you can also consider further generalization. So namely, a set of natural numbers S, which runs from A1 to AM, is said to satisfy the property dkn if two distinct number plus n is a kth power for any distinct I and j, and k greater than or equal to 3. And then by, in this case, it's related to the case of superelliptic curve. Namely, it will actually give you a solution to this superelliptic curve, right? Where this k is bigger than or equal to 3. And then you can have factor which runs from a1x plus n to amx plus n, right? Or you can also have less factors than this fx. And then what we know is that by Falting's theorem, this kind of curve has finitely many integral points, right? And then there are many known properties about this dkn, but especially for when n is equal to 1 case, if we define our mkn to be the supremum of the size of such S, which satisfy the property dkn, what's proven, for instance, is that when your k is 3, so namely when you have y cubed on your left side, then the size of the set with property M31 or property D31. So namely, if you take, which gives +1 equal to some sort of cubic number, that set should have size bounded by 7. And when your k is 4, then it should be bounded by 5. And when your k is somewhere in between 5 and 176, then that size of the set should be bounded by 4. And in general, for big enough k, that will be just uniformly bounded by 3, which tells that the size of dk1 tuple is bounded by 3 for large k. So there are some results like this is known. But in fact, there aren't that many results known about this, this kind of generalization. But what's interesting is that it's kind of correlated to Falting's theorem, and then you have some sort of finiteness already. So that's like 3 different ways to generalize our Diophantine M tuples, namely by, so the first version was just D1, and the second version was Dn, still where your k is 2. So you're only considering the square numbers. And then moreover, you can generalize in the way that you're adding n and then consider any power k, where k is greater than equal to 3. So yeah, there are several generalizations in this context. So yeah, so how can we study this? There are many ways to study this, but in this project, what I'm interested in is its connection to the bias conjecture. So bias conjecture is stated in a little technical way. So that's a conjecture arising from elliptic curves, which is formulated in the thesis of Steve Miller, who is one of the other collaborator potentially for this project. So if you're let your fk to be one parameter family of elliptic curves over Q, which means we already defined our elliptic curves, namely y squared equal to fx, where fx is a degree 3 polynomial. And then what I mean by a one parameter family is that your fx will have its parameter k in its coefficients. So whatever k value you're plug in, you're going to get an elliptic curve over Q. And we denote by AKP to be the choice of Frobenius. In other words, that if you consider like modulo prime p, then what you're going to get an elliptic curve over QP or FP. And then if you compute the value of the prime p plus 1 minus that number of elliptic curve over FP, then you're going to get some sort of number like AKP. Then using this definition, we also define the Arth moment sum associated with the Fk and prime p in the following way. So your MRP Fk is going to be defined by the sum over all possible values k inside of the finite field Fp of AKP over to the power of r. So in particular, if you consider the first moment, by definition, that will be defined as just the sum of all AKP over all possible values of k over Fp. And then your second moment is going to be defined as AKP squared summed over k over Fp. And the bias conjecture says something about this M2PFK value. And then these quantities are kind of difficult to compute in general, but one can calculate them kind of explicitly in some lucky cases. And then those lucky cases are stated in like the papers which we posted on the this project page. But you can kind of see those computations using this Legendre symbol and so on in order to compute the second moment of those family. But more precisely, in the rest of this introductory talk, I would like to kind of maybe elaborate more on the statement of the bias conjecture. So more precisely, what we know is that our second moment, M2PFK, can be described as the sum of P squared plus F3P, F2P, F1P, F0P, where the absolute value of FIPs are going to be bounded by C times P to the power of I over 2, where your I runs from 0 to 3. Then the bias conjecture states that if you let your Fk be a one-parameter family of elliptic curve over Q, then the largest index I of the terms FIP in the expansion of M to PFP, such that this, if you define your mu I to be some sort of average of FIP over P to the power of I over 2, if that's a non-zero value, then that will satisfy the condition that this mu I is going to be negative. So say if you use if you use index 3, and then if you get this mu3 value to be non-zero, then the bias conjecture is saying that that mu3 is negative. Whereas if you get mu3 to be 0, so namely there's no bias in the moment of this FIP over P3 over 2, then what the conjecture is saying is that if you go down to the second largest index 2, and if your mu I, which is the average of F2P over P, is non-zero, then that will actually be negative. And also same for index 1 and index 0 too. So the bias conjecture really says that there is going to be some non-trivial bias in the way to compute the second moment of AKP. Is the statement of bias conjecture clear enough? Okay, if there are no more questions, I can also introduce why we are considering the bias conjecture. So namely, if you consider an elliptic curve EK, which is the form y squared equal to this kind of degree 3 polynomial in X, where this K is the parameter, as you can see. And then this kind of strange elliptic curve appears in the discussion of the Diophantine M tuples. And then that actually gives an instance of a family which satisfies the bias conjecture, which is very surprising. So on the other hand, the reason why this kind of elliptic curve comes out is very, it's kind of complicated to state right now. So we are going to slowly learn about it in the first couple of weeks and how that can prove the bias conjecture. So if you want to know more about this, please join our project group. And then that's the end of my introductory talk. Are there any questions before I stop sharing the screen?
Yeah, could you also tell us a little bit more about how this project is gonna proceed? Like, how many weeks do we spend on learning this stuff, and how many weeks do we spend on like figuring out stuff?
So I think for the first 3 weeks, we are probably just going to intensely learn about things. But afterwards, I think our project should be kind of 30% learning new stuff and then 70% research. So, you know, doing the research is not really only about solving problems, but also it's about learning the materials you need while doing research, right? So, yeah, so that's roughly our plan. The 3 weeks of learning and then kind of doing research along with learning about something else.
Will you go over this again during the project?
What do you mean over this again?
Like the main.
I can't hear you very well.
I mean, will you go over what we spoke again rigorously during the project, or is this somehow a prerequisite for the project?
It's
Are we
not the
supposed to be
prerequisite.
knowing this completely?
No, I'm not supposing you to
Before entering
learn. No, I don't suppose you to know about this material very well. Yeah.
Along the lines of how the program will run, I know that a lot of the stuff about bias conjectures and correlations and various things like that, there's a large portions of number theory that are still conjectural, and some of the work is still kind of computational. To what degree is our work likely to be focused on doing like computer modeling simulations, approximations, and trying to compute stuff versus to what degree will we be focusing on trying to?
So it really
prove
depends
stuff?
on you. I don't have anything in mind right now, but if you're more interested in like computational aspect, that would be great. I'm more used to the theoretical part of this this theory, but at the same time, if someone is willing to study about, you know, the models and the computations and then how this can be computationally generalized, I think that would also be a great project to work on.
I'm also kind of more interested in the theoretical stuff, which is why I wanted to figure out. So thank you.
Yeah, sure. But, you know, a project should be half theory and also half computational. So whichever way should be great. Yeah.
Yeah.
Are there any more questions?
You might have already covered this, but around how much prerequisite knowledge should we know and in what topics?
I don't really expect anything from you right now. But depends on your prerequisite. Maybe you would have different kinds of questions you're going to work on, I would say. Does that answer your question?
Yeah, thank you.
I'm a bit late. I want to ask that how can I apply for this project?
Sorry? Oh, how are you going to apply for this project? I think that's what Adam mentioned before.
Actually, I'm a bit late. That's why my friend gave me the Zoom link. That's why.
Okay, so how about watching that, and then probably that will give you an answer. And also for the logistics, I would recommend to contact Adam for that.
Thank you so much.
Where would the recording be? Would that be through email? So we can watch this again.
Oh, for the recording.
Oh, yes.
I can.